Welcome everyone, thank you for joining. I am Stavros Tseranidis, structural engineer, and I'm going to present to you structural shape optimization with parametric square root functions. Regarding the motivation for this research, as we all know, design of large-scale construction projects involves a plethora of different parameters and constraints, and structural optimization is an important goal. However, it must always respect and be performed in harmony with all the parameters and constraints of the project to achieve the architectural intent and aesthetics. Of course, the ideal scenario is to have the form factor and the structural and functional considerations develop all simultaneously from an early stage. But how can a structural shape which has already been molded by different multidisciplinary requirements and is at an advanced level of design and coordination be modified and optimized to increase its structural efficiency without compromising the architectural intent and the requirements? A new methodology of structural shape optimization through the use of parametric square root functions is proposed to address this question, and this is the formulation of the function. This methodology cares of this scenario that is often occurs in practice, and it provides an opportunity to create efficiency while the design has been through some coordination and some design stages. This is a scenario which occurs in practice, and this is a methodology to solve that. Now, regarding the parametric square root function formulation, it's the main formulation is that the span of the structure is from minus b to b, so essentially that's a constraint, and then also the maximum allowable increase in the structure's height is also a constraint, and through those two constraints you define this function. Now, a little bit about the evolution of the concept. One way you could meet those constraints was through piecewise linear functions, but this is not differentiable at the axis of symmetry, and it's also non-parametric. Also, the parabola, while it is smooth on the right here, it is also non-parametric, meaning that only one parabola can fit those constraints of span and maximum height increase. Now, the parametric square root function formulation proposed can achieve results between those two of the piecewise linear and the parabola while allowing the designer some flexibility. The constraints ensure that of the span and the height ensure that the parameter of the function is only one, so it's a bit easier and more flexible for the designer. Now, I want to present some case studies. The first case study is about long span roof with regularly spaced steel beams of sinusoidal shape. The span is 10 meters. You can read more details of the formulation and the parameters in the paper. Now you can see the original structure on the left and the modified structure with the shape functions on the right. The maximum height increase was 1 meter, and yet a reduction in the maximum deflection under live loads of 77% was achieved, and also the maximum moment was reduced by 55%, while you can see the shape of the sinusoidal form has been preserved. Now, for the second case study, I want to show some space frame long span roof structures. There are two scenarios examined here to cover some variety of form, and you will see that again the increased structural efficiency and the overall shape are achieved. The span of the structure is 40 meters, and the maximum increase of the height is 2.5 meters in this case, and you can read more details about the structural system in the paper. Now, for the first case study, it's this shape, and you can see again the comparison between the original and modified structures. Again, you can see a dramatic decrease in the maximum deflection of 51%, while you can see even from the top view that the form remains at first glance very similar, which is the intent of this methodology. The steel quantity also gets reduced in this case by 12%. Another form factor here also achieves great reduction in the maximum deflection, so an increase in stiffness while the form is preserved, and the reduction, a significant reduction of the quantity of steel as well of 21%. Another case study is for a different structural system, the grid cell, which I just wanted to test if it can perform in different structural systems. So this system works through moment connections between two layers, while the other was axial only truss. The span was the same, and the results were again very, very good in terms of deflection, moments, and steel quantities. And the overall shape, as you can see here, and you can see some more views in the paper, is preserved. So overall, the proposed methodology can achieve advances in efficiency and stiffness while preserving the shape, and the methodology can be applied at advanced stages of design, and it's a mild touch intervention methodology. Some aspects to consider are discussed in the paper, and so please read through the discussion if you want to find out more information. So overall, this methodology is a new methodology with parametric square root functions. It can be applied at advanced design stages, and some case studies to implement it have been presented. Thank you very much for your attention, and I look forward to discussing more with you. Thank you.